Let C be a curve parameterized by the vector function out of t, which is equal to x of t comma y of t comma z of t, where t is between a and b. Then under proper assumptions, the length of the curve C is given by the integral from a to b of the function, which is the square root of the quantity dx dt squared plus dy dt squared plus dz dt squared. Let's do an example. So let's say I want to find let's say we want to find the length of the curve C, where C is given by this vector function out of t, which is equal to cosine ti plus sine tj plus tk. So the components of this vector function are cosine t, sine t, and t. Here t is between 0 and 2 pi. To find the length, first of all, notice that the x component of out of t is cosine t, so I'm going to label x is equal to cosine t, y is equal to sine t, and z is equal to t. So as a result, dx dt, the derivative of x with respect to t, would be negative sine t. dy dt, that's the derivative of y with respect to t, that's cosine t. And dz dt is the derivative of z with respect to t, which is 1. So we know that the length would be the integral from 0 to 2 pi of square root of dx dt squared. So this is going to be the square of dx dt would be sine squared of t plus dy dt squared, so we get cosine squared of t plus dz dt squared, which is 1. Now from trigonometry we know that sine squared of t plus cosine squared of t is 1, so here we get root of 2. So then we get the integral from 0 to 2 pi square root of 2 dt, and if we evaluate this integral we get 2 root 2 pi. So we see that the length of the curve is equal to 2 times root 2 times pi. I want to mention that we know that this vector function traces the curve exactly once, because if you look at the third component t, the z is z as a function of t is increasing as so as t progresses from 0 to 2 pi, you know, the z coordinate here increases from 0 to 2 pi. So as a result, clearly the c is traced exactly once. Okay, so that's the end of this example, and I will see you in the next video.